Carnot cycle also then defines for us the maximum coefficients of performance for refrigerators and heat pumps. Okay, so the idea is, here's a question. So you're designing a refrigerator for Australian conditions. You feel like it might get up to 45 degrees in the kitchen or into the space adjacent to the fridge. And you want to keep your milk cold, and so you're having a low temperature reservoir of 2 degrees. So the question is, what's the Carnot coefficient of performance for a refrigerator based on these temperatures? So how efficient can you be? And then you find a fridge advertised with a coefficient of performance of 4. Is that good? I don't know. Is that close to the Carnot efficiency? Is it not? How do you know, how does a consumer, what's the thing that indicates to the consumer the coefficient of performance for a given refrigerator or fridge, freezer, that sort of thing? Star energy rating, right? The number of stars relates to the coefficient of performance. It's not a one-to-one relationship because you wish it was. I read the standard that defines it, thinking, oh, I could present that to the class, it would be really practical. It's a horrific read. But it relates. There's a bunch of stuff, but the star rating system will give you an indication of the coefficient of performance. And the question is a COP of 4 good? Well, sounds good. Put in 1 kilojoule of energy, get 4 kilojoules of energy out of the cold space. So similarly, based on the heat engine, so each process is reversible, heat's transferred reversibly. It's a fantasy, but that's what we've done. So we can't build these in practice, but they give us something to compare to. So for our beta for thermal efficiency, that was our formula from before. For the Carnot cycle only, our ratio of heats equals our ratio of temperatures. We've seen that derivation. So the coefficient of performance for a refrigerator for the Carnot cycle is this formula here. Last year, I would have recommended you memorize this. This year, I'll provide formula sheets. The formula sheet for the final exam will be larger than the formula sheet was for quiz 1. So that's the maximum. It's good. I want you to talk. Nothing like a quiz. So that's the best thermal efficiency you can have. The heat pump has a similar thermal efficiency. It's 1 plus whatever the beta is, for what it's worth. Right, so we get the same relationships as before. Here we're using T's instead of Q's, and that's only true when you deal with a Carnot cycle. For a heat engine, the larger the temperature difference, the higher the efficiency can be. So the larger the ratio of temperatures, so 900 and 300 is a third. Okay, so we lose a third of what we could produce. If you could get something that was between 1200 Kelvin and 200 Kelvin, you could get to 6, right? You'd lose 16% of the, you'd have a Carnot efficiency of 84, for example, right? For refrigerators and heat pumps, it's the other way around. So the closer the temperatures are, the higher the coefficient of performance will be, okay? So for example, here, if you get, as TH on TC gets close to 1, right? TH is always going to be higher than TC because it's the hot and the cold, right? So this is always going to be larger than 1, but as it approaches 1, this approaches infinity. Same with the heat pump. As this approaches 1, so TC is always going to be less than TH, okay? But as that ratio approaches 1, the coefficient of performance approaches infinity as well. So it's harder to move heat between temperature reservoirs that are further apart in temperature. It's easier to move heat between reservoirs that are closer in temperature as a ratio. Just something to think about. How do I remember the formulas? I remember that formula. It's not such a big deal, but I think you should know. I think you should have a sense for what these formulas are, and I think they're worth remembering in any case. I remember it has to be a ratio, and I want this value to be between 1 and 0. Okay? So I need 1 minus I need this to be something that's less than 1. And the way to get the TC and the TH as a ratio to work that's less than 1 is you put the TC on the top. So I derive all my formulas on the fly as I go, which is why I need lecture notes, because it's awkward to see. The coefficient of performance for a refrigerator is the reciprocal of the coefficient of performance for a heat engine, if you take the absolute value. And then the coefficient of performance for gamma is just beta plus 1. So that's how I do, when I'm answering these questions, that's how I do that. So there's only really one formula to remember, and the rest are based on principles. So what is the maximum theoretical thermal efficiency for a refrigerator operating between those reservoirs? Let's have a look. Beta equals 1 on. Yeah, that looks right. 1 on 1 minus the cold temperature is 2 plus 273.15. The hot temperature is 45 plus 273.15. I have to go to Kelvin because I'm dealing with a ratio. If I was just summing and minusing, or particularly minusing, if I was just taking the difference of two temperatures, I wouldn't need to go into Kelvin. The fact that I'm taking a ratio means that I need to go into Kelvin. And I did this calculation beforehand. It comes out at 6.40. So for every kilojoule of work we put into this refrigerator, in an ideal sense, in the Carnot sense, we would get 6.4 kilojoules of heat out of the cold space. And how much heat would we put into the hot space? 7.4. Yep, good, excellent. So then we say, well, the refrigerator you're buying has a coefficient of performance of 4. What's the second law efficiency? And so is 4 good or bad between these temperatures? There's our thermal efficiency. And we say our second law efficiency, okay, eta second law, is whatever our actual device is operating at divided by what the Carnot would say that it should be operating at, which is 4 divided by 6.4, so 62.5%. So you're 62.5% of the way towards an ideal cycle. And we'll get a sense for, and particularly your assignment will give you a sense for, is that good or bad? Right? What's the air conditioner in this room operating at in terms of its second law efficiency? How close to Carnot are we operating? What's the temperature outside? Cool day, 25? We're trying to maintain 20 in here, right? What's the ratio in Kelvin between 25 and 20? Our coefficient of performance should be more than 10. What's the air conditioner operating at? I don't know, but you can actually, I haven't seen it for this building, but I went and looked at the condenser units on J17, and it's written on there. The high pressure, the low pressure, what refrigerants it's using. You can Google a refrigerant, get the table data. Right? You can reverse engineer the refrigerator for J17 at least, because you can access the condenser. I assume you can here also. You can do it for your domestic one at home as well. So we now define second law efficiency as our actual performance divided by our Carnot performance, and we'll note that the heat engine will always be less than Carnot. Refrigerator always be less than Carnot, heat pump always less than Carnot. There's a bunch of exercises in RISEL that basically say, someone comes to you and says, they've got this temperature difference and they want to get this much work out per cycle. Is this possible? And you do the Carnot calculation and you say, no, they don't know what they're talking about, or yes, it's possible. And I think the PSS has some questions about that as well. So it says, is this possible? Where we say, if it's less than Carnot, it's possible, and we can work out the ratio. If it's getting better performance than the Carnot cycle would get, it's not possible at all. So we've done Carnot for heat engine. I just wanted to point out that it also exists for the refrigerator and the heat pump case. Write the formula incorrectly into the OneNote document. This is what the math should have looked like. TH on TC minus 1. That gives you the value of 6.4. It's now updated in the OneNote document. So apologies for that. So what I'm trying to say here is the efficiency or coefficient of performance for any real-world device will be less than, and these should be less than symbols, not less than, equal and. Theoretically, it could be equal to, but really, no, they're not. Will be less than the Carnot thermal efficiencies between the same temperature reservoirs. So to give you real quick and dirty, is this even theoretically plausible, right? The Carnot coefficient of performance or efficiency is a really easy calculation to do. I just did it incorrectly a few minutes ago. No, but it takes, it takes 30 seconds to crunch the numbers, the high temperature, how hot does the hottest point get, how cold does the coldest point get, give me the Carnot efficiency, right? These numbers, we'll actually need to analyze the cycle to get these. And that will take a longer time. Typically, a final exam for this subject used to be 3 hours. There were 3 thermal cycle questions. So 1 per hour, typically, right? It takes about an hour to solve a relatively complex thermal cycle question. And out of that, you might be asked for the thermal efficiency, and that gives you this number on the left, okay? So Carnot gives you a very quick and dirty, how efficient could this possibly be? Analyze the cycle, that gives you the number on the left, and then you can take the ratio of the two numbers and say, okay, well, how close is our cycle getting to the Carnot efficiency? Okay, so that's the, like I said, coefficient of 4, that sounds great. How great is it? I don't know. Carnot gives us something to compare it to.